So the title might be confusing, but we're going to be doing a bit of a Christmas carol for computing. The past, the present, and the future of computing, and what I think of all of it. So for those of you who who are not tech savvy, let's start with the ghost of computing past. Humans have been making devices that count in primitively at least for as long as we've existed, more or less, give or take, since civilization, let's just say. Um, the first truly like mechanical calculators and like counting machines started coming up in the ancient times. Mainly first emerged in the Middle East by the Arabs and certain Eastern Asian cultures. They were ahead for a long time with little machines that could calculate the position of the sun, for example, or the stars, and map them out with gears and sprockets and whatnot. Those were, hugely, obviously expensive and very limited in scale at the time. But they were way ahead of whatever Europe had to offer. They were too busy inventing beer. But anyhow, fast forward a bit, and we get to more or less what a normal person would start to imagine when they think of a computer in the 1800s, with mechanical counting machines and tabulators. I'm not a historian, but I will place the first emergence of modern computing in the 1840s and 1890s, which was earlier than most of you might think, but let me explain. One of the figures I want to talk about is a lady called Ada Lovelace. She was a brilliant mathematician and a really smart person overall, and she is attributed for coming up with a lot of modern binary logic, along some very impressive mathematical foundational stuff as well. But I'm not going to get into that; not my field. Um, um, and the other event that I think really triggered the advent of modern computing was actually something that you might not immediately think of, which was the 1890 U.S. Census. A census is just a sort of a questionnaire that gets filled out by everyone in a nation to see how much is the population, what's the gender distribution, what's the age distribution, well, how's the income looking, that sort of thing. Back then it was done on manual, script paper, whatever. 1890 rolls around, and the U.S. government realizes that they have more and more people being born in the country, to the point where counting them by hand is an option, and traditional counting machines just isn't cutting it because it's taking them several years to calculate one census, and if they do one, each 4, 5, or 10 years, well, we're going to get to a point where the data that they have on the census will be an entire generation behind, and they can't have that. So they decide to put out a contract, a government contract, which are, they throughout history, a lot of great inventions come from government contracts. They're nice and juicy. In this case, the company who was given the government contract is one that you may or may not be aware of, which was IBM. I believe they went under a different name back then, but IBM, for those of you who don't know, was basically Microsoft before Microsoft. They were the business computing company. They made large computers for big companies who need to crunch data and do a lot of math and store a lot of data, like banks and laboratories and offices and things like that. So that was a pretty important event. The first time you had, arithmetic and math and calculation at scale. Mind you, at this point, we still didn't have electronic computers. So this was all, done by relays and things like that. So we're talking about multi-ton, ginormous, monolithic computers who could only do, probably less than even the cheapest, nastiest calculator in the modern era. I mean, you could probably get like a $5 calculator from a supermarket, and it would outdo anything back then. Fast forward and you get to some more known folks. Um, there was a lot of computing history between 1890 and 1940s, but I'm not smart enough to know any of that. So I'm gonna go with what I know is that Alan Turing. If you haven't heard of him, he basically invented not only the idea of a modern computer, but also the rules and the logic that we still go by for most part. He was a brilliant mathematician, and he really liked solving puzzles and things like that. And I think he did some set theory stuff, but I'm not quite sure. He also he has a really interesting paper on the pattern that appears in different animals like leopards and butterflies, which is really interesting. Very multi-talented guy, but for our purposes, he was in the British forces during World War II, trying to decrypt the messages that Nazis were sending between them, and he managed to invent the Turing machine that could, decode any message that the Nazis gave them, given the key. And that was huge. The fact that they could crack the code basically won the Allies the war. Mind you, that and 7 million USSR soldiers. But hey, it wasn't an easy one to win. So yeah, after the world got rid of the Nazis, at least for a while, Alan Turing continued his work on computers. Not only did he invent, very fundamental basic logic, but he also came up with the idea of very important computing rules. He had this idea of an abstracted Turing machine. The idea was, if he was given infinite magnetic tape and a machine with, one or several data pointers that could, punch a hole or fill the hole on the paper, what would the capabilities of that machine be? Given infinite resources, what could the machine do? Would the machine still be constrained by the limits of binary rules, for example? And one of the things that he came up with was the halting problem, which was the idea that even if you had a machine with infinite resource, a Turing machine, which is essentially a computer, that there would still be programs that would be impossible to know if they would crash or halt or not before running them, which is really interesting as well. I'm not doing him injustice. The guy is brilliant, and you should go look into him yourself. I highly suggest it. But moving forward a bit, I want to talk about some other, perhaps lesser even unsung heroes of computing. I'm going to pull up their name because I don't want to screw anything up. I want to talk about the ENIAC 6, which are widely regarded to be the first computer, or at least software engineers ever. They were working in the U.S. Military, and it was a group of 6 brilliant women: Jean Bartik, Frances Betty Holberton, Kathleen Antonelli, Marilyn Meltzer, Ruth Tiltelbaum, and Frances Spence. And these 6 people were given room-sized computers by the U.S. military, like room-sized. They're said to be like between 20 and 30 tons. That's metric tons, I believe. And there were no programming languages. There was no software environment. There was no OS. There was no terminal, right? So how do you program a computer like that? Well, you go in there and you flip physical switches and screw around with physical cables and dials and have physical circuitry for the logic gates and whatnot. And those 6 used a lot of heavy math to figure out how to build the ENIAC, which is, perhaps the first or one of the first sort of large scale computers used in military or government. The first electronic, I should say, electronic programmable computer, which is really, really impressive. Obviously, that goes without saying. The other person is a more known one, which is Grace Hopper, who's regarded to be one of the, the most important, influential programmers of all time. She worked again in the military, in the U.S. military, in the 50s. She invented COBOL, which is an important programming language, and she actually wrote the first compiler. If you don't know what a compiler is, it's a program. It's the program, I should say, that turns human readable text code into zeros and ones, like binary code that the machine can execute. Because computers don't know human language; they only know binary code. So you have to have some sort of intermediary, which is the compiler, that translates the human readable code into zeros and ones. So that was a huge attribution, and I do mean huge, humongous, because suddenly the field of computer science went from something that required you to, manipulate cables and circuitry and dials and switches and levers to be able to write your code, to something more tangible, something more human readable and writable and more expressive. So that's very important. In fact, even right now, some banks and like super important old infrastructure runs on COBOL, which I think is really cool. There's some other really important people in computing history. I want to keep this video relatively short, so I'm going to try to summarize only the history part in this video, I think, and then move on to the future in the next installment. So I think this video will stick to only to the ghost of computing past. So moving forward a bit more in time, the Bell Telephone Company, which in modern era is also known by AT&T, they had this laboratory called Bell Labs. In fact, I have a book on it somewhere here. There we go. The Idea Factory, Bell Labs, and the Great Age of American Innovation by Jordan Gertner. Great book. In here, there's some really cool pictures and stuff from the first ever building for Bell Labs, as well as the people who worked there. I'm not sure how many of these are copyrighted. One of the most important things that Bell Lab invented is the birth of the semi-transistor. Look at that. It was just a piece of wire and some germanium metal and a penny as a conductor. If you don't know what a semi-transistor is, it's an electronic device that allows only a little bit of current to pass through, depending on what you're applying to it, the voltage, I believe. If you're wondering what it's used for, well, if you have a semi-transistor, then you can use multiple of them to switch on and off to represent zeros and ones. And if you get enough of them, you get an iPhone. A modern computer has several trillions of these semi-transistors, and we make them at the nanoscale, which I think was either 10 to the power of -9 or -12 meters. In fact, IBM recently put out some research going into how to make them almost under a nanometer, which is ridiculous to think about. Nearing the size of the atom of the material they're making it out of, which is, silicon. But in this book, they talk about some other very important inventions. So that alone would have been enough to put them in the history books forever, right? They then moved to a bigger building somewhere in what was it, New Jersey? This one right here, which is which is also the filming location for the hit Disney, um, sorry, the Apple TV Plus um, TV show called Severance, and they came up with several very cool inventions. One of them being they concepted the idea of video calling all the way back in 1964, but that's not what we're here for. We're here for computing. So let's talk about computing. They had some very important people. One of them being Claude Shannon. Claude Shannon, who is, well, you know, Claude by Anthropic, the AI model. This is who he's named after. Claude Shannon was a very important mathematician. He's probably the father of machine learning as and among very some other very important inventions and discoveries. But Bell Labs, they just have Claude Shannon, who basically came up with the idea of neural networks as machines and whatnot. But they also had some people called Dennis Ritchie, and I don't want to get his name incorrect, and Ken Thompson, who were the inventors of the C programming language, which I don't know what computer you have right now. It could be a phone, a smart fridge, a BlackBerry. Like, it doesn't matter what you have right now. It runs C code. It's such an important language, and it's a great language. It was actually considered a high-level language. So, if you're wondering what a high-level and a low-level language is in programming languages, the idea is that it's not a skill level thing, although it kind of is. A low-level language means it's closer to the machinery. It's closer to machine code. It's less human readable. And a high-level language is more further away, more verbose and human languagey, if that makes sense. And C, when it came out, was actually considered to be a very high-level language because the syntax for C is like so verbose. It's like you use English words and whatnot. Although now it's considered a low-level language because you manipulate machine memory, for example, directly. But that's not the only thing that Bell Labs came up with. They also came up with Unix, which is the first ever OS, basically. The funny part is that C, Unix, and the next invention I'll talk about from Bell Labs all came about not because of some like market research or whatever. It was just a bunch of nerdy people put in a very big laboratory, and they came up with things to solve their own problems. Unix, for people who don't know, is a kernel. A kernel is the fundamental base level program that helps you as a human interact with the computer and works as an intermediary. It translates whatever you give it as commands for operation on the computer. So if we just go back for a second, we had people like Grace Hopper give the ability to write code and have it translated into zeros and ones. And now in 10 to 15 years time, we've gone to the point where you can give commands to the computer that aren't necessarily code. You can just say things like I don't know, like write, name.c to disk, SDA0 or whatever, if that makes sense. You can now give the computer commands that are not necessarily entire programs that you have to write. Unix continued to evolve over time and was picked up by a guy named Linus Torvalds in the 90s, a student of Aalto University, I believe, here in Europe. And what happened was, well, he sat down one day and decided that he wanted to have a super customizable operating system for himself, and wrote Linux. Linux being the backbone of most modern servers and things, and I run it on my personal laptop, and you should too, mind you. It became the basis for different OSs like Android, and a piece of the Linux kernel is now in Windows 11, I believe, via the Ubuntu subsystem. Um, so it's really funny how the first ever OS is still around. In some form, I mean, you can probably argue like Ship of Theseus, but like in some form, the Unix kernel, which was the first OS, is still around. There have been OSs after Unix. There will be more after Linux for sure. But the fact that we're still using it at any capacity is incredible to me. But moving forward, so Bell Labs currently has a ridiculous portfolio, right? They have the semi-transistor, arguably one of the most important inventions of human history, alongside fire, right? And writing. And semi-transistors, we make quadrillions of them per year for your phone, your smartwatch, even your light bulb, right? We had the C programming language, the most popular programming language of all time, probably. Don't quote me on that. And they have Unix, the first ever, and still relatively like untouched and still used kernel slash OS. And they have one more concept that's less talked about, but I think is equally important. So just put yourself in the mindset of a laboratory attendant in Bell Labs, okay? So imagine you're a mathematician, and you have only one big computer for doing your calculations and stuff with your colleagues, and you all have to share one, right? Well, how do you share a single big computer? Well, it's tough. You could go there physically, do your operation, and walk back to your desk, but no one wants that. Because what if it's on the other side of the campus? Or what if you're just a little lazy, right? So the solution was, okay, we can have one big computer, but we can give each person a small terminal. A terminal being a small computer screen, I mean a TV screen most likely back then, because they didn't have dedicated computer monitors. A TV screen with a keyboard and a lot of cables going back and forth, and the idea is on the screen you will see the output of the computer, and your message will be sent across cables a long distance to get to the computer, and you can message back and forth. Great. Well, what if you have multiple people, maybe the guy next to you, right, on his desk, also trying to access it at the same time? Well, now you need to have a queue. So you'll have to send some commands, add that to a queue of commands, and then as you process them, shrink the queue, and everyone takes turns, etc. Well, that is on paper fine, right? You have a queue for commands, and then everyone waits their turn. But human nature isn't like that. We're a bit impatient. So what do? How do you solve this problem? Well, if you don't have the budget you can't just buy more big computers, right? More workstations. So the solution that they came up with is a system. I don't remember the name of it, unfortunately. I'm not sure how much of it they speak about in this book. No. Well, the idea for them was you would send your program to be compiled, or you would send a command. It would get added to a queue, but what would happen is it would be a rotating queue. So what would happen was you would go to the first person's command or request, process a little bit of it, and then skip to the next person. Process a little bit of that, and then skip to the one after that one. And that way, what you had was you gave people the illusion that their program was being executed in real time, when in reality they were adding artificial delays in between that would cut out and restart execution. Resume, I should say. But that was enough for the researchers to be happy. That was enough for them to time share on the computer. And that is arguably the backbone of modern cloud computing. It's the same logic that is used when if you're a developer, you might, for example, use Vercel or Railway for hosting your code, or AWS. But even if you're not a tech savvy person, or don't care about tech, you might be on Google Drive, or you might be um, running and executing commands without knowing on a cloud computer. You might be accessing files remotely. You might be editing documents on Google Docs, and all of them still lay on the fundamental idea set forward by these people. The idea that multiple people can share one computer at scale just by introducing some artificial delays and tricks so that the computer is occupied at a reasonably equal amount for each person. Um, so, as I said, I don't want to keep this video in too long because this will be the longest Geiger talks by far. What I want to conclude is a small intro into the ghost of computing future with quantum computers, because the acceleration in quantum computers seems to me to be very similar. Back in the day, in the 1840s, as I explained, we had mechanical, huge relay computers that occupied entire rooms. At some point in the 1910s and 20s, they became small enough that you could put them in an office. In the 40s and 50s, we invented electronic computers with magnetic tapes and whatnot. And those were again room size and humongous, like the ENIAC. Then they became small again, small enough that companies like Casio and Sharp were able to make them small enough to be like desk side. In fact, as a quick side note here, in the 70s and 60s, it was pretty common practice to have office computers where you would have a desk where the underside was the computer because it was so heavy and large, and then the top side would be just like a normal, like nice wood trimmed desk surface, which was really funny, but cool. And then we had fully digital computers coming out in the 60s as well, but again they were room sized, and hard drives were impossible to make small, and they were like barrel sized, right? Well, suddenly in the 80s and 90s, digital computers shrank again. And, now they're small enough that we can fit them in, not even the palm of your hand, not even this, right? We can make them as small as they go, basically. They're smart devices with, for example, an AirPod, like any Bluetooth ear set, has more computing power than almost any computer made 40, 50 years ago, probably. And the chip in it is small enough that you can lodge in your ear without noticing, right? So probably yay big. And now, in the 2010s, we start seeing the first ever quantum computers. And again, they're room-sized, they're heavy, only laboratories have them, and they seem like they're impossible to shrink down in size. When have you heard this story before? A lot of people doubt the utility of quantum computers because they're like, well, who would own one? Right? Who would own a quantum computer? What use do you have for it? And how would you sustain it? How would you maintain one? Well, that was the same argument for the ENIAC and the Cray supercomputer and many like it. Back when we were transitioning to mechanical computers, we had the same problem. They were room size and enormous. And if you asked an average Joe in the 60s, hey, you want to buy one of these in 20 years' time? Yeah, you want to buy a digital computer? They will say, what are you talking about? What's a digital computer? What would I do with it? Well, 20 years later, in the early 80s, we had PCs, and some were even small enough to put in a suitcase. Compaq actually made like the first, I don't want to say laptop because they were still too big, but they were essentially a suitcase-shaped computer that you could take around with you. It was cool. And well, now quantum computers are in the same area, I feel, in the same position. They're too big. They're impossible to maintain. There are no, you know, end user applications. I mean, laboratories use them for research and whatnot, and simulation, but the average person has no utility for one as of yet. And it seems to me like history will repeat itself once again. Um, and I think, just to conclude this very long video, I think it's important to put more attention to quantum computers. Because what they are, at least currently, are slightly non-deterministic. At least, wait, they destabilize over time. Some of them do. Most of them do. All of them do. Which give incredible parallel compute power. And if you think about the sort of compute that AI needs, which is again non-deterministic parallel compute at humongous scale, that is what a quantum computer does best. I'm not even saying that everyone will have a quantum computer, although we probably will, if history is to be believed. Um, I think it's important to realize that the solution to our current AI crisis, on the one half, the economic factors are terrible. Companies are investing billions and trillions and not getting almost any money back. In fact, I think Amazon is the one of the biggest spenders, and they have lost like 300%. It's actually crazy. Um, and the other factor is the environmental factor and the data privacy and ownership side of things. I'm not gonna get into the data side of things because I feel like that's pretty obvious to anyone who's actually looked into this issue. The environmental factor is really sad because not only are we spending all the electricity on AI, but just making the components alone is just a lot of CO2, and building out all the ginormous data centers and whatnot. The thing is, back in the 60s and 50s, when we were transitioning to digital computers, we didn't have a need for them at this large of a scale, right? I mean, we did for compute, but there wasn't some sort of like bank run bubble that was going on, unlike the AI evolution, the revolution. Um, there's all these companies who are willing to pay hand over fist for memory sticks and GPUs and afterburner cards, and there simply isn't enough silicon or resource to keep up with demand. Um, if this might be even nerdier than the things I've talked about in this video so far, but some open source models, because we don't know actually how big the AI models used by OpenAI and Anthropic are. We can guesstimate, but that's about it. But the most powerful Chinese models are open source and open weight, and they're over 3 trillion parameters. I'm not an AI expert, so I can't tell you exactly how big a parameter is, but a parameter is like a neuron. It's like a node, basically. So you have to compute and iterate over 3 trillion nodes for this one AI model. And the size of the average AI model has basically 10x in the last 2 years. Let me check. Yep, about a year and a half, 2 years. And if this continues, well, we're gonna be having 30 trillion models by the end of next year. And there simply isn't enough GPUs on the planet to sustain that amount of expansion. And I think the answer is becoming awfully obvious. If we want to save the planet, obviously having less AI use will be nice, but let's be honest, humanity has never done that. We've never taken into consideration the environmental impact when new technology emerges. It will save electricity and modern plastic products and computing in general and cars and planes and air travel. So we, unfortunately, as much as it would be nice to hold our horses for a second, that's not gonna happen. Um, so I think the best route forward is to one make AIs that are more efficient, but perhaps more effective will be to accelerate quantum computers and research into quantum computers, um, because they fulfill each other just so nicely, right? AI needs a lot of parallel compute, non-deterministic, at scale, and quantum computers provide exactly that. I'm not an expert, so I can't tell you how hard it would be to say port over an AI model or library like Llama CPP, I think CPP, or Llama or whatever, which is based on Llama CPP actually, over to a quantum system. Because, well, there is no universal standard for quantum computers as of yet. Everyone's doing their own little thing. Some are doing photon based quantum computers, some are doing particle based, ion based, whatever. I've even seen laser based with photons, which is really cool. All of which work fundamentally differently, but hopefully on the high level will work the same to get some sort of common ground established. The closest thing that we have to some sort of quantum computer universal guidebook, I think, is IBM's Qiskit. It's a Python. It's not a library. Some people simplify down Qiskit to a library. After looking into it a bit more, it really is sort of like an evolution, a diversion of Python that works for quantum. And that's my hope. There simply isn't enough silicon and investor money out there to sustain AI in the long term without absolutely wrecking our planet. So my hope will be to, done what we've done so far with computing history, and evolve quickly, and get quantum computers out the door, and hopefully look back at this, 5-year patch of history as a weird little era where quantum computers weren't quite there, but AI was. So we had to make this patchwork infrastructure where we were building masses and masses of inefficient computers that are ultimately deterministic, while AI is fundamentally non-deterministic. That will be it for officially the longest Geiger Talks video I've ever done. I suspect no one will get this far. There's no way. I've rambled for entirely too much. But thank you for watching regardless. Like, subscribe, give me a cookie, send me money, I don't know. Thank you for watching, and I'll see you in next time.